Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of apartment hunting. This is a very cool question for two reasons. The first one is that it's got a sort of canonical, less optimal solution and more optimal solution. The less optimal one is the sort of easier one to immediately identify, but it's actually quite tricky to code out properly, as we'll see in the rest of the video. And the second, more optimal solution is one that you can sort of derive once you've implemented that first one, typically. The second thing that's kind of cool or unique about this question is that you are given a lot of information in the prompt, some of which is actually not at all useful for the problem. And that's often done in interviews because the interviewee is sort of tested on their ability to be able to parse the prompt and identify what information is actually going to be useful and what information is actually not going to be useful for them. So with that said, let's dive into the problem and things are going to become more clear. So the problem gives you two inputs. The first one is a list of hash tables, and this list represents blocks in a city. Because the idea is you are going to be someone looking for an apartment, hunting for an apartment, and you want to find the perfect apartment for you. So this list, at every index, you can imagine that you have a different block in the city. And every hash table in that list represents the buildings that are either present or absent at a given block. So as an example, you might have a block where the hash table has two properties in it, one that says office and the other one that says school. And if the office maps to true, then that means that there is an office present at that block. If the school maps to false, that means that there is no school at that block. So here in front of me here, I've got an example of this input array. I've done a little extra step here, which is that I've only put like these letters here, or these initials, all represent the buildings that are actually present at the blocks that map to true in the respective hash tables at each index. So here, the extra step that I've done is basically I've removed any buildings that map to false in the hash tables. And so this is sort of what I was saying in the beginning of the video when I said that there's information that is actually unnecessary in this problem. Here it happens to be all of those buildings that map to false. You can almost ignore them entirely. They're irrelevant for the problem, but we'll see that a bit more later on in the video. As I was saying, the second input is another list, this time just of building names, and these are the building names that matter to you. So here in this case, we've got G for gym, SC for school, and ST for store. And these three buildings matter to us. What does that mean? That means that we are trying to find the perfect apartment amongst all of these blocks, and you can imagine that every single block also represents an apartment. Basically, there's an apartment at every block. And we want to find the block that has an apartment that is going to have to walk the least amount of distance to reach all of the important buildings. In other words, here, gym, school, and store matter to us. So we want to find an apartment that is situated at a block where all of the distances, the maximum distances to get to these important buildings are minimized. And so the answer is going to be 3. Index 3, which is right here. So this is the answer, the position that I'm circling. Why? Because as you can see, if you're at index 3 at this block or at this apartment, you've got the gym, which is an important building to you, 1 block away. You've got the school, which is an important building, literally 0 blocks away. And you've got the store, 1 block away. So in total, the maximum distance that you would ever have to travel to get to all of your important buildings is 1 from your apartment. Conversely, let's assume that we were looking at index 2. Here, you would have the gym and school super close, but you would have to walk 2 blocks to get to the store. And similarly, if you were at index 4, you would have the school and store right there, but you would have to walk 2 blocks to get to the gym. So All that to say, that is the question. Now let's try to solve it. So as you can imagine, the first thing that sort of comes to mind is that we're probably going to have to iterate through these blocks or through these apartments and sort of calculate distances, right? Try to see how far away things are, how far away our buildings are, and so on and so forth. And that's exactly what we're going to do. So you can imagine that one way to approach this would be to iterate through all of the blocks. We start at 0, and we iterate all the way to the end, to the last block at index 4. And at every block, we go through all of our required buildings, right? So like, let's say we start at this block. When we're here, we say, okay, let me iterate now through all of my required buildings. And we would start with the gym, for instance. And then I'm going to reiterate through all of my blocks to calculate the minimum max distance to get to the gym from index 0, right? So I'll just repeat that one more time. You iterate through all the blocks. At each block, you say, okay, I'm going to go through all of my requirements. And for all of the requirements, I'm going to reiterate through all the blocks to see where is the closest one to me, right? So for example, here we start at index 0, and we iterate through all the requirements, starting at gym, and we say, how far away is the closest gym? How far away is the closest gym from index 0? So here we would iterate again through all of the blocks, and we would clearly see that this gym at index 1, at block positioned at index 1, is the closest gym to index 2. So it is 1 block away. And so we would write that down here, 1 block away. Let me actually move this line, because now we are going to go through the school requirement. So this is 1 block away. Then we go through the school requirement. We iterate through all of the blocks here again, and we say, how far away is the closest school from index 0, our current index? And it's right there. So it's 0 away. So we'll put 0. Then we can, let me just select that. Then we can say, how far away is the closest store? And the closest store is actually pretty far away. It's 1, 2, 3, 4 blocks away, right? The closest store to index 0, our current index, our current block, is 4 blocks away. So we're going to write that down right here. And now we're done going through all of our requirements for the first block. And so what we're going to say now is, how far away, like we have all the distances of the closest of each building that's important to us. The gym is 1 block away. The school is 0 blocks away. The store is 4 blocks away. How far away is the farthest one of these buildings? And here it's pretty obvious that 4 is the greatest of all these values. Basically, we take the max value of these 3 values here. And so we're going to be able to now say, let's erase 1, 0, and 4, and we're going to be able to now say, I'll write it in orange, that at index 0 here, if this were where we wanted to buy our apartment, we would have to walk 4 blocks if we wanted to get to all the buildings, because there's at least one building that is 4 blocks away. The closest of that building is 4 blocks away. Okay? And now we continue doing this for all the blocks. So here I went kind of slowly, but now we'll pick up the pace a little. So if I move from index 0 to index 1, now we iterate again through all of the requirements. So how far is the closest gym from index 1? It's 0 blocks away, because we're literally on a gym. How far is the closest school from index 1? Well, we would iterate again through all of the blocks, and we would see there's one school here, which is 1 block away. There's another school here, which is 1 block away. And then there's 2 schools 2 and 3 blocks away. Okay, so the answer is 1. The closest school from this block is either right before or right after, so it's 1 block away. And finally, we go to the store. I guess I should erase these 2 lines here. We go to the store, and the closest store from block 1 is, or block 2, I guess, at index 1, is 1, 2, 3 blocks away. And again, we iterate through the entire blocks to find that. There's no other way to do that programmatically. So now here it's 3. So now, once again, we say, we know that the closest gym is 0 blocks away from index 1. The closest school is 1 block away. The closest store is 3 blocks away. What is the farthest of all these closest important buildings? Once again, it's the store, 3 blocks away. So we're going to say, okay, 3 for index 1. In other words, like if we pick an apartment at index 1, we will have to walk 3 blocks to get to all of our buildings because one of them is at least 3 blocks away. The closest one of that type. So here we can already see that index 1 is going to be better than index 0, but that'll be for after. Okay, we move on. Now we go to index 2. We do the same thing, go through the gym, the school, and the store. So the gym is 0 blocks away, because there's one right there. The school is 0 blocks away, because there's one right there. And the store is 2 blocks away. So now we can say, okay, the value to put here is going to be 2. So we will erase this, and that. We can also erase this line here and store 2. So far, it seems like the more we go to the right, the better our apartment is. Then we move on to index 3. And here, just to remind you one last time, what we're doing is we are iterating through the entire array of blocks. Then at each block, we are iterating through the entire array of required buildings. And then for each of those, we're reiterating through the entire array of blocks to find the closest distances. So here, the closest gym is going to be 1 away. The closest school is going to be 0 away. The closest store is going to be 1 away. So the maximum of all 3 of these values is 1. So we can store 1 here. We can erase now all 3 of these. And then finally, we are at the final index, index 4. And here we can say, okay, the closest gym is 2 blocks away. So you can see the closest gym, we have to go back 2 blocks in the back. The closest school is 0, and the closest store is 0, because we are on an apartment block with both a school and a store. So the biggest value between all 3 of these is 2. If we get an apartment at index 4, we will have to walk at least 2 blocks to get to a gym, the nearest gym. And so now we are almost done. We have all of these values, which represent the max distance that we would ever have to walk from the current block. And we can pretty easily find the minimum of those values and return the index at which that minimum value is located. And so here, you can see that the minimum value is 1, and the index is 3. And so that's why the answer is 3. So that's the first way to solve this problem. Again, on the one hand, it's sort of simple to come up with, and it is, fairly straightforward. On the other, it is kind of tricky to code out, as we'll see soon enough. There's going to be, 3 nested for loops and a few, comparisons that need to be, positioned correctly. But now we have to ask ourselves, can we optimize on that? So to know if we can optimize on that, we should, of course, do the time complexity analysis and the space complexity analysis of this question. So as far as time is concerned, the time complexity is going to be O of b squared r, and b represents the number of blocks that we have in our list, and r represents the number of requirements that we have in our list. Why is it O of b squared r? Well, think about it. We're doing 1 iteration through all the blocks. That's O of b. Then for each of those blocks, we're doing an iteration through all of the requirements. That's O of b times O of r. And then for each of those, we're reiterating through all of the through all of the blocks. So that's going to be another O of b. So O of b times O of r times O of b squared r. And in the mix of these for loops, because these are going to be for loops, or these iterations, we are going to do a few comparisons, comparing what values are smaller or what values are bigger or whatever. But those are going to be constant time operations. So overall, time complexity O of b squared r. As far as space complexity, the space complexity is going to be O of b, because the main thing that we're going to be keeping track of in an extra list is going to be these numbers here, the max distances for the blocks. And we're going to store those in an array, and at the end we're going to use them up. We're going to use them up to find the smallest value. Now, the more I think about it in a hindsight, maybe we could actually optimize this. And here I'm really improvising. After, like, now that I'm actually walking through the problem, I'm realizing maybe we don't need to store this entire array. Maybe we can simply keep track of a variable that says like smallest distance and keep track of the index that it's at and sort of overwrite it every time. But for now, we're just going to go with O of b space. But do keep in mind that optimization. Maybe you can even implement it. I'll leave it to the viewer to implement it themselves. But okay, can we improve on this, right? Can we do better? And the answer is yes, we can. Now, first of all, I guess, yes, we just saw that maybe we can do better from a space point of view, but we'll put that aside for now. But can we do better from a time point of view? Now, it seems like we're probably going to have to iterate through all the blocks and all the requirements once, right? This seems sort of like inevitable since we have a bunch of blocks and we have a bunch of requirements and we know we have to kind of, do stuff with them. But the thing that bothers us here is this square, the b squared. Like, do we need this b squared, or is there a way to eliminate it? One way to think about this is that third for loop, where we sort of iterate through all the requirements and then reiterate through all the blocks so that for each requirement, we can find the nearest requirement, the nearest building of that requirement and find that sort of closest distance. Is there any way that we could somehow pre-compute that such that our iterations are then fewer, such that we have to iterate through the array fewer times? And the answer is yes. So basically what I just said about pre-computing, that's really going to be the technique that we're going to use. We're going to use a technique that can be very applicable in a lot of algorithm problems. So keep this technique in mind just in general when you're in your interviews, especially when you're dealing with these problems, let's say with a list, and you've got a bunch of for loops to compute values. Ask yourself, maybe there's a way to pre-compute values and then sort of optimize like that. Here the idea is, Imagine, I guess I'll erase also all these numbers here in orange, but imagine for all of our requirements, the gym, the school, and the store, we already knew all of the distances, all of the sort of closest distances from each index. So what I mean by that is, imagine, how should I order this? Maybe I'll erase these here and put them to the side sort of vertically. Imagine we had gym, school, and store. And imagine for the gym, we knew that at index 0, the closest gym was 1 block away. At index 1, the closest gym was 0 blocks away. At index 2, the closest gym was 0 blocks away. At index 3, it was 1 block away, and at index 4, it was 2 blocks away. Then imagine we knew that for the school, at index 0, it was 0 blocks away, 1 block away, 0 blocks away, 0 blocks away, 0 blocks away. And for the street, we knew that here we were, I keep saying street, store. We knew that this was 4, 3, 2, 1, 0, right? If we had these values, which these values we were computing in that sort of third for loop, right, in our previous solution. But if we had these values, we could literally just iterate through all of the blocks and say, hey, at index 0, take the maximum of these 4 values, or of these 3 values, which is 4. So I'll circle it here. At index 1, take the maximum of these values, which is 3. Here, take the maximum of these values. Here, take the maximum of these values. Here, take the maximum of these values. right? So we compare sort of all of the values at a given index, at a given block of all of these, and we immediately find the answer. And so here, again, imagine we were given these three arrays here, then the solution would then just be O of BR time complexity, because we would do one iteration through all of the blocks, and at all of the blocks, we would compute the maximum value of all of these rows here, and there are how many rows? R rows, based on the number of requirements, right? Now, how do we can we pre-compute all of these values in a way that is time efficient? And the answer is yes, because, or basically, I guess, let me rephrase that. If we know that if we were given these values, we could have a time complexity of O of BR, right, as opposed to B squared R, then we just have to find a way to compute all of these values in a time complexity of O of BR or less to make this actually valuable. And can we do that? Yes, we can. Let's see how. How do we compute all these values, right? Well, we would do it probably requirement by requirement. So we'll start with G. Can we compute, because basically if we can compute this, like this entire row here, in O of BR, then we've found a better solution, because then that means we can do it for this, then that means we can do it for this, or rather, let me rephrase, if we can compute this row in O of B, not O of BR, then that means that we can do all of these computations R times, which will be O of BR, and it won't add to our final time complexity, and we'll be good. So let me undo that. So how do we compute all of these values in O of B? Well, we're at the gym. We can do one pass through the blocks from left to right, where we say, keep track of the closest gym that came before me. So like here, it would be, there's no gym here. Here, it would be, oh, there's a gym and it's a distance of, okay, let me redo. Here, we'll put an X. There's no gym here that came before me. Here, there's one and it's 0 away. Here, there's another one and it's 0 away. Here, there's another one and it's 1 away. It's right before me. And here there's 1 and it's 2 away. And now we go from right to left. So we start here at the end and go back to the beginning. And we say, is there a gym here that was before me? No, there isn't. So the closest gym is 2 blocks away. Now we go to index 3. Is there a gym here before me? No, there isn't. So the closest one is 1 block away. Then we go here, okay, 0 away. Then we go here and we say, wait, there's a gym that was before me here. 1 block away. But wait, we already had found a gym here that was 0 blocks away from the first pass when we went from left to right, right? Yeah, that was 0. So 0 is smaller than 1. So we know that here, the closest gym to index 1 is here 0 blocks away. And then we go here and we say, okay, the closest gym that came before us when we were going from right to left is 1 block away. So we can erase this X and see that there's a 1. So the point is, we just did that. We just calculated all of the values that you see in this row in O of B time by just doing 2 iterations of O of B time. So O of 2 times B is O of B in the blocks array for the gym. And then we do that for the school. Then we do that for the store. So that's our computations of O of B time. So that's O of BR time. And we know that then we can just iterate through all of our blocks. And for all of our blocks, say, hey, what's the maximum of these values? And here we have to go through, we have to compare our values, right? Like 1, 2, 3, there are 3 requirements. R is equal to 3, so R comparisons. So that's going to be O of R. And then we do that for every block, so O of BR. And so in total, we have found a time complexity of O of BR time. And the space complexity for this solution is actually going to be worse than the previous one. The previous one was only O of B. because we found, the final array, this final array. But here, it's actually going to be O of B plus O of BR, because we are storing all of these. We are storing R arrays, right? One array for each requirement, and each array has B length. So in total, this is going to be O of B plus BR space, which is B times R plus 1, right? O of B plus BR is B times R plus 1, which is just BR. So O of BR. Okay, so we have found a way to optimize this, the first solution, by doing pre-computations. And this made our space complexity a little worse, but it made our time complexity a lot better because we got rid of that square. Now, of course, this is the kind of thing that in an interview you would have to kind of talk about with your interviewer, tell them the trade-offs, and they would appreciate it very much. Now, I realize that this might have been still a little bit confusing. I think that it'll make a lot more sense once we dive into the code. So without further ado, let's jump into it. All right, so we've got our apartment hunting function defined. It takes in a list of blocks as well as a list of requirements. And this is going to be the first solution, the one with 3 for loops, the one that's a bit less optimal. So the first thing that we're going to do is declare this array, right? The array that's going to take O of B space. And that array is gonna hold at every block the maximum distance that one of the buildings is at away from this block, right? So this is going to be max distances at blocks. As an aside here, I do want to say that this question is kind of tricky as far as naming goes, because it's very confusing to wrap your head around that, the fact that we have, we have like the closest of a given required building at a certain block, but then we're looking for the farthest of all of the closest required buildings, if that makes sense. So it's really important to come up with good names here, and even if they are good names, to explain them out loud to your interviewer. So anyway, max distances at blocks, and we're going to initialize this to be a list of the size of the blocks array. And we're going to have every value start as -infinity. That way, when we do the maximum of a value currently stored in the array and another value that we compute, we know that if we have -infinity here, we'll always pick the other value. So this will be float of -infinity for block in blocks. Perfect. And now we're just going to begin our triple for loop. So remember, we start by iterating through all of the blocks. So for I in range, len of blocks. Now, the reason that we are iterating through the indices rather than just through the blocks is, remember, we're also going to be then iterating through the blocks again once we iterate through the requirements, and we're going to want to calculate, the distance between 2 indices, for instance. So we definitely want to keep track of the index that we're at. Now, for every block that we iterate through, we then iterate through all of the requirements. So this time here, we just need the requirement. We don't need the index of the requirement. So for rec in recs. And then here, remember, at each requirement, the thing that we're really doing is we're saying, what is the distance of the closest of this requirement? Right, so for instance, for the gym, what is the distance of the nearest gym? Where is the nearest gym? So here we're going to declare a variable that we keep track of, and it's important to put it under this for loop, right? Under the for rec in recs for loop. And that is going to be closest rec distance. This again represents the nearest gym, for instance. It starts at float infinity, not float infinity. The reason we're initializing this to infinity as opposed to -infinity is here we're looking for the closest gym or the closest rec. So we're probably going to use the min function, right? We're going to be comparing 2 values and taking the minimum of 2 values at every iteration. And so initializing this to +infinity is just going to make our code a bit cleaner. And now we iterate again through all of the blocks. So this time for j in range len of blocks. And now here we say, hey, at every block, let's first check if the current requirement that we're at or that we're checking for, like the gym, is located at that block. Is it present at that block? So if blocks at index j, and remember, these are hash tables. So this is a hash table, right? So if blocks at index j, property rec, the requirement, is true, if that maps to true, and we can completely ignore the ones that map to false. So if blocks at index j of the requirement is true, then the closest rec distance, right? So like we have a gym at this given block, for instance, then the closest gym distance is going to be equal to the minimum value between the closest rec distance. So that's where this infinity initialization comes in handy. And the distance between this particular requirement or this particular gym and our current index I. And so here I'm probably going to create a helper method called distance between, and it'll just take two indices, I and j. This is just going to make our code much simpler. I'll write it right now. But def distance between, it's going to take two values, a and b. This is really like a completely abstracted out method. And all it's going to return is the absolute value between a and b, right? Because the distance between 2 points is their absolute value. That way, here, as a side note, I want to make a point here about like clean code. This is a perfect example where a lot of candidates won't think of making a helper method for something like distance between. And here they'll get wrapped up in a lot of ugly lines of code, like, oh, we have to handle when the index j is smaller than I and we have a negative number, or when the index j is bigger than I and we might have a negative number there, right? So making this a helper method and calling it distance between, or get distance, which is very readable, just makes their code a lot cleaner. Anyway, so now we've said, okay, for every block, go through every requirement or every building, every gym, store, school. For all of them, go back through all the blocks and keep track whenever you do find that requirement, if it's the closest one to index I. And then finally, right, once we're out of this for loop, but when we're still in the requirements for loop, here we want to update the max distances at blocks. So we're going to say, hey, max distances at block I, at this block, we've just calculated what the nearest gym is, or we've just calculated what the nearest store is, or what the nearest school is. We've calculated the distance to the nearest one of these requirements. So for instance, the nearest gym, I think in our answer, was like 1 distance away. The nearest school was 0 distance away at index 3. However, sometimes, the nearest store, or I guess let me rephrase. When we were at index 0, rather, I think the nearest gym was right there. It was like 0 distance away. The nearest school was 1 distance away, or maybe it was the opposite. And then the nearest store was 4 distance away. So the only thing that matters at that point is what the max distance of all the nearest requirements is. And so here we're going to say max distances at blocks at I is going to be equal to maximum, we're taking the maximum, of whatever we currently have there. And that's why this is very nice to have the negative infinity stored at the beginning here, because that means we don't need to handle that case. And the closest rec distance. So again, to clarify what we're doing exactly here, and this is why this problem, even the sort of less optimal solution, is non-trivial. But so here what we're doing is we're saying, okay, we just got the closest rec distance. We just got the closest store. Okay, the closest store is 4 blocks away. Well, at our current block I, we also knew that the closest gym was 1 block away. Okay, so what is the maximum distance to get to the nearest requirement? Well, it's the maximum of whatever the maximum gem was, which was 1, and the maximum distance, or the nearest store distance, which is 4, and so it becomes 4, right? And that means that now, at this block, we would have to walk at least 4 blocks to get to one of the nearest requirements. Now, once we're done, now we're really done with the 3 for loops, and now we can just return the index of the block that has the minimum max distance, because remember, we want to find the apartment from which, or the apartment block from which we would have to walk the least to get to the nearest requirements. This problem is very confusing. It's a very meaty problem. But so we want to return the index at which we find the minimum value in this array. So there are a lot of ways to do this. Probably the clearest or most readable way is just to do it kind of, iteratively and verbosely. So we'll create another function. It's going to be get index at min value. Get index at min value. And we're going to pass max distances at blocks. And that's going to be it for our apartment hunting function here. And so here we'll define this function. So def get index at min value. It doesn't have to know that this is max distances. This is just an array at this point. And so we can say, index at min value equals 0. Min value equals float inf. Again, we do the same sort of like hack with float inf that sort of allows us to not have to handle the very first case when we're comparing numbers. For I in range len of array. We check the current value, of course. So current value is going to be equal to the value at index I in the array. And if the current value is smaller than the min value, then the min value is equal to current value. And then the really important thing that we care about is the index. Index at min value equals I. Whoops, not idea, I. Okay, cool. And then we return the index at min value. So here, just to re-clarify, we say, hey, let's start with the index of the min value at index 0. Let's say our min value is float inf. By the way, this could be anything, right? This could be like none if we wanted to, but might as well make it an integer. And we iterate through the entire array. We check the current value, check if it's smaller than whatever a min value is. At the beginning, since this is infinity, we will always hit this if statement and go inside, update the min value, update the index at min value, and return it. And that's it. This is our first solution. It's actually quite clean. Like, it's written pretty well, and it just reads kind of like English, and it's overall kind of nice. There is some complexity here with this closest versus max, and min versus max, and all that. But overall, that's the first solution. And like we said in the conceptual overview, it runs in O of b squared r, or b squared times r time, and O of b space. And the reason it's b squared times r is because we're doing one for loop of length b, where b is the length of blocks, one nested for loop of length r, where r is the length of the requirements, one other nested for loop of length b, so hence the b squared times r. And in this for loop, we really just do constant time complexity checks. Here we've got another constant time complexity check. And then finally, we return this array, or this call to this method, and this just iterates once through our final array of length b. So that's, it's b squared times r. In theory, it's b squared times r plus b, but that is just the equivalent. That is the equivalent of, b times b r plus 1. So we can kind of remove this 1. So it's really b squared times r, and the space complexity is going to be O of b because we've got this max distances at blocks array that is of length b. And in it, we just store integers. So that's the first solution. Now let's jump into the second solution, the one where we sort of optimize stuff. And this one is going to be a little bit more meaty, to be honest. So I'm gonna comment all of this stuff out. And this one is going to be a bit more meaty, or a lot bigger, let's put it that way. So we'll start with the same function definition, right? Apartment hunting, and it takes in blocks as well as requirements. But if you remember, the first thing that we do here is we pre-compute all of the nearest gyms, all of the nearest schools, all of the nearest stores, all of the nearest requirements, basically, at every single block. So here, again, the naming is going to be kind of tricky. It's very important to kind of explain to your interviewer how you're naming the variables and what they represent so that they don't get lost. We'll say min distances from blocks is going to be equal to a list stemming from a map where we map the requirements. And when we map the requirements, what do we map them to? Well, we map the gym to all of the nearest distances of gyms at each block. We map the stores to all of the nearest distances all of the distances of the nearest stores at each block. So here we'll do a lambda function, right? That takes in a requirement, because we're mapping the requirements, and that maps each requirement to, and here we'll create a helper method called get min distances, passing in blocks as well as the current requirement. So to clarify, and now we're going to write this helper method, what are we doing here? We're saying the min distances from all the blocks is a map of the requirements, right? We're mapping all of the requirements. So this is going to be like an array of length 3 or a list of length 3, where for each requirement, we get all of the minimum distances of that requirement from every single block. Okay, so then if we write out, and here we're going to be doing some other stuff, I'll pass for now, right? But if we write out get min distances is going to be our pre-computation method, and it's going to do that sort of like start to finish pass, right? Or pass from left to right, iteration from left to right, and then from right to left to pre-compute all the values. So this get min distances method is being called on a given requirement, right? And so we're saying the min distances are going to be, let's initialize them to 0 for block in blocks. And so let's see, right? We're trying to find basically what the closest index of the current requirement is for the given block that we're at. So the closest, we'll do the same sort of hack that we did before. The closest rec IDX is going to be equal to float infinity. And what we'll do is we'll iterate first from left to right, right? So for I in range len of blocks, we say we're iterating from left to right. Let's see if the current requirement is actually present at every block. If it is, so if blocks of I at rec is present, then when we're going from left to right, we know that, when we're going from left to right and from right to left, we know that whatever if it is present, then this is sort of the closest requirement, the closest of that requirement in this direction, right? Because let's say, imagine you've got an array that's like, gym, store, gym, school. I'm just giving an example where there's only one building per each thing. At index 0 here, we're looking at gyms. Let's say we're calling get min distances on gym. Here, if gym is at index 0, then we know that the closest rec index of gym is 0, right? So now we can just say, okay, closest rec index is equal to 0, so it's equal to I. And here, to be honest, the more I think about it, I think we don't actually need to initialize this to float infinity. This can actually be initialized to anything. this is really the float infinity here. It's not the same hack. I sort of got confused there. We can initialize this closest rec index to anything we want. This can be this will probably be like 0 for now. Or maybe I guess we will. Maybe the reason we initialize it to float infinity is if we then calculate the distance between. Yeah, I guess we'll calculate the distance. Okay, let me continue on with the code, and I think this will maybe help us in the near future. So we say, okay, the closest gym right now is whatever the current index is. And now we can say, okay, we're passing from left to right. So the min distances at index I is going to be equal to the distance between index I and closest rec index. So I'm actually going to copy paste this function here. I'll copy paste this function here. Let me delete this. So here we're saying we're going from left to right. We're looking for gyms right now. We're getting the min distances of gyms. If we have a gym, then we know that the closest gym is located at this index. And min distances of I at index I is going to be equal to the distance between I and that closest index. That's sort of it's very simple we can like very sort of naively say this because we're going from left to right. We're kind of ignoring everything that comes after us. Now, of course, this might lead to an incorrect value, but we will then come back and do a pass from right to left. So for I in reversed range len blocks, right? So we're doing a pass from right to left now. If blocks of index I and rec, so if we have another gym or another rec, then again, the closest rec index in this direction is going to be equal to I. To be honest, maybe this would be better named, in this direction. This becomes a little bit verbose, so I think I'm going to just keep it closest rec index. But the point is here, the closest gym in the direction from right to left, right? And now here, this is the tricky part. We're going to copy this line, right? I'm going to copy this line saying the min distances of a gym at index I, right, at this current block. Here, this time, it's going to be the minimum between whatever we currently stored from our first pass and the distance between calculation. So does this make sense? Like, the idea is this, right? If we have, again, our array, which I'll rewrite one last time, gym, store, school, gym. Here, we just said, okay, like our min distances array here for gym is going to be kind of 0, 0, 1, 2, 0. That's sort of from the pass left. From the pass right, it's going to be 0. Then here, we go here and we say, okay, we have 2 here, but we had this closest index. There was 1 right here, which is 1 distance away. So what's the minimum value between what we have here, 2, and the distance between the closest index from this direction, which is 1 away, which is 1. So the minimum value between 2 and 1 is 1. So here, this is going to be 1. And similarly here, it's going to be what is the minimum value between 1 and 2, because this gym is 2 blocks away from here. So here it's going to be 1. Take the minimum value, right? And then here, 0 and 0. So hopefully now this makes sense, right? This is how we can sort of find, this is sort of annoying to write in reverse order. But so hopefully now you can see sort of like how we're computing the minimum distances in just O of B time, because this entire method here is going to take O of B time, right? All we're doing are 2 O of B iterations through the entire blocks array, and then we're doing, constant time operations here. And finally, we can return the min distances array. So here, what we've really done is we've computed this type of array. This is what we've computed in get min distances, and we've computed this for every single requirement in this map here with the lambda function. So then the next step here, we go back to the path, is to say, okay, we have the min distances. Now we want to find the maximum distances at each block given all of the minimum distances of each requirement. Again, very confusing. You have to voice everything to your interviewer so that they don't get confused. So we're going to call this max distances at blocks. At this point here, we're really calculating what we had calculated up here in the first method, but we just did this pre-computation. That's the main difference. And so here I'll probably do another helper method just to make this very clear. So get max distances at blocks, and we will pass in the blocks as well as the minimum distances from the blocks. Okay, I'm going to write this down here. Def max distances at blocks. We can pass in the blocks and the min distances from blocks. And so here what we're really doing is we're saying find the maximum, again, I'm going to repeat it, find the maximum distance of all the nearest distances of the blocks, right? So this is going to be an array, max distances at blocks equals, this is supposed to be a method, so get max distances, right? Yeah, get max distances. Okay, so this is going to be initialized to 0 for blocks in blocks. And what are we going to do here? We're going to iterate through all the blocks, right? For I in range len of blocks. And we're going to say, okay, the min distances at the blocks. Right now we've got, I keep deleting my arrays, but we had, for instance, we had like 0, 0, what was it? 1, 2, 1, 1, 0, I think. That was sort of the array that we had for the gym. These were the minimum distances of the gyms before. We've got like a bunch of these, right? We've got a bunch of these. So what we want to do, we've got a bunch of these for all of the requirements. What we want to do is we want to say the minimum distances at a given block, because we're iterating through all of the blocks, is equal to a list of, again, a map, right? We're mapping these minimum distances from blocks. And how are we mapping them? We're using a lambda function. Lambda, the distances, and we're mapping the distances. Wait, what am I doing? Lambda, the colon comes here. We're mapping the distances to the distances at index I. So let's try to parse this line to make sure that we're not making any mistakes. We've got these minimum distances from blocks, which are all these values. And we want to say we're iterating through all of the blocks. And we're going to say the minimum distances at a given block is a map of all of these things to the minimum distance, to the values at that index. So basically, this would be for a value below. Let's assume these are our values, or maybe let's make them a bit more realistic. Let's do, like, I don't know, something like this, right? And like this. So here for index 0, this would be 0 to 0. Right? At index 0, like this. And then index 1, this would be 0, 3, 4, and so on and so forth. Does that make sense? So it's like kind of the first column, the second column, the third column, and so on and so forth. And then what we do is just max distances at blocks index I equals the max of the min distances at block. So I'm going to reiterate this function because it's very confusing. Again, you kind of have to sit down and wrap your head around it, but it does make sense. It makes a lot of sense. But remember, we've calculated all the minimum distances from the blocks. So here we've got all these arrays. This says, hey, at index 0, the closest gym is 0 blocks away. At index 1, the closest gym is 0 blocks away. At index 2, the closest gym is 1 block away. Okay, we get it. At index 0, the closest school is 2 blocks away. At index 1, the closest school is 3 blocks away. Okay? At index 0, the closest store is 0 blocks away. At index 0, the closest store, or index 1, the closest store is 4 blocks away. Okay, we get it. Now we're saying, for all the blocks, iterate through all the blocks, get an array of all the minimum distances at a given block. So in other words, get 0, 2, 0, or get 0, 3, 4, or get 1, 1, 1. Right? Get those columns. And this is the closest gym. This is the closest school. This is the closest store. And then get the maximum value of all these three here. And once we do that, let me delete this. We store this in an array here at index I. And then finally, we return max distances at blocks. Oops, distances at blocks. And now we really have the exact same value that we had in our very first function and the less optimal one. We have these max distances at blocks. And so here we can just do, we can just copy paste this, I think. We can return up here. We can return our get index at min value, right? Because now we have all the maximum distances and we just want to get the smallest one. And then we can copy, I guess, this method. So let's copy it and we'll put it, I suppose we'll put it up here or down here. Let me uncomment it. Okay, so now let's calculate the time complexity. Here we are getting all the minimum distances from blocks. So we do a map of all the requirements. So that's going to be already O of R, right? Where R is the length of requirements. We map to get min distances for every requirement. Get min distances creates a new array of length B. So that's O of B. One loop O of B, constant time operations in there. Another loop O of B, constant time operations in there. Distance between is a constant time operation. So we've got a total of 3 O of B operations here, because remember, initializing this array is O of B, but 3 O of B is O of B. So this here is O of B, right? Then here, get max distances at blocks. We've got all of these min distances from blocks, right? We create one new array of length B. Oh wait, sorry. This is not O of B. This is O of BR. This is O of B. This is O of B. Okay? But this is O of BR. And here we create one thing O of B. Then we iterate O of B. Here we do a map. Let's see, what do we do here? We do a map of all the min distances from blocks to whatever value at index I. This here, this lambda function is a constant time operation. But we map over the min distances from blocks, and this is an array of length R, right? This is an array of length R, very important. We had like 3 arrays, right, for the gym, the school, and the store, for instance. So this is an O of R operation. This is a constant time operation, but our O of R operation is multiplied by O of B. So this here is O of BR. Again, and this is O of B, so O of BR plus O of B. You can remove that B. So this is O of BR. And then finally this, get index at min value, we had said it before, this is just O of B, right? So this is going to be O of B. So 2O of BR, you can remove the 2. Plus O of B, you can remove the B because that's just O of B multiplied by R plus 1, right? O of B multiplied by R plus 1. You can remove the 1. So O of BR. And so O of BR is R time complexity. So I'm going to put it up here. O of B multiplied by R time. And for the space complexity, I'll remove this for now. For the space complexity, what is it going to be? Well, the space complexity is going to be O of B for our final array, like this thing that we compute. And then we have these min distances, like these min distances from blocks. There are of them. There's one for each requirement, and each requirement has B values for every block. So it's O of BR. So O of BR, again, O of BR plus B for this max distances, but again, you can remove this B. And that's it. That's O of BR space. And so as you can see, this method is just this. Let me just delete this for my own sanity. I always like to have everything sort of be perfect. This method or this solution is much better from a time complexity point of view because we removed the square here, the B squared. It is worse from a space complexity point of view, but that's just something definitely worth talking about with your interviewer. This question is really cool, but it is very difficult. I'm realizing even more and more now that I'm like sort of typing it up and going through it, that, yeah, this is just like a super difficult question. And it's the kind of question that I think if you were in an interview, you might be expected to come up with this one. You might be expected to code out this solution. And then you might be expected to have like a 10-minute conversation about this solution, or at least try to come up with it. But you would likely not be expected to fully code out this solution just because, this video alone, I think we're at 35 minutes right now for this entire code walkthrough. And you can imagine that you wouldn't have time in a 45-minute interview to come up with all the solutions and code them out, this perfectly when it's the first time you see this problem. Anyway, I hope that you found this problem very informative. Hope that you found this video informative, and I'll see you in the next one.